Buenos días a todos. Entramos en la siguiente presentación de la sala 2. El tema o el título de la presentación es Steering Advisory System for Rotary Steerable Systems. De los presentadores de otros, Nasli Demirer, V. Umut Saluhoglu. Oh, no, excuse me. I have moved. Excuse me. Giuseppe. Excuse me. The wrong page. Okay. Again. Synthetic oil consumption, remote monitoring through operational data, Aeroderivative Gas Turbine application. Authors, Giuseppe Salerno, Ilaria Parrella, Carmine Allegorico, Domenico Iasparro. Baker Fuge. Begin.
Hi, good morning and good afternoon, everybody. This is Giuseppe Salerno, and I'm working for Baker Hughes as a lead data scientist. And today we're going to see one application on our aeroderivative gas turbine regarding the synthetic oil consumption remote monitoring. Okay, let me go on. And the laser pointer, just a second. Here it is. Okay, so we are going to have an introduction about the problem itself, then the description of the problem on the synthetic lube oil system. Then we are going to see how the problem was assessed through the technical development, some results, and finally the conclusions. So before doing that, I would like to tell you a little bit the environment where I'm working. I work in the Remote Monitoring and Diagnostics Center of Baker Hughes. Basically, we provide a service, a monitoring service that works 24 hours a day, 365 days per year. So we provide a monitoring service on our assets. So we do anomaly detection, we do also some reports, and we have, as per today, around 1,500 assets under monitoring. Our assets comprises turbines, aeroderivative and heavy duty, and compressors, centrifugal compressor, reciprocating compressors, and so on, and also some steam turbines. So this is, let's say, the environment where I'm working on. And we have 3 hubs, one in Houston, one in Florence, and one in Kuala Lumpur, that covers the 24 hours per day. So what is our process? Basically, we acquire data from our site continuously. So this is something that happens continuously, live. We process this data through our analytics, and the analytics identify potential failures that are sent, and an alert is sent to our diagnostic engineers that perform an assessment and decides if it is necessary to call the customer and the site operators to fix the problem, or to open a service request on a level 2 engineering support. And finally, we provide also some periodic reports on the assets. So let's now go on. Okay, the synthetic lube oil system is one of the most important systems for our aeroderivative gas turbine. In fact, the synthetic oil system is made basically by these components that we are seeing here. Basically, we have a tank level that measures the level of the oil in the tank, and this is for us a good sensor, let's say, a good measure to establish the consumption rate. Then we have 2 pumps, one a supply pump and another one is a scavenge pump that brings the oil from the tank level, and it put it through bearings, VSB systems, and some auxiliaries. And this is in the correct lubrication and cooling performed by the synthetic oil is very important for these components. So the monitoring of this system is very important for our machine in order to monitor the performance, the reliability, and the availability of the turbine itself. So we received, we basically translated the needs that came from diagnostic engineers into some requirement for our for our analytic. The analytic is the monitoring system. So the main goal of the system is to continually estimate the actual synthetic lube oil consumption rate based only on tank level measurement. The analytic should be able to detect both abnormal consumption and leakages, which are quite different in terms of signatures, and we're going to see that later on. And this consumption rate can be then used also to do a fleet analysis. So it's very important for the reports that I was talking to you about. Then the analytics, since we have a lot of assets under monitoring, we have more than 300 aeroderivative gas turbine under monitoring in our M&D centers. We need an analytic that is able to self-adapt and self-tune based on the tank level measurement type. I mean, there are different kind of machine, different kind of operations, different kind of sensors, environment, and so on. And the analytics should be able to adapt himself automatically based on the sensor. As you can see here on the lower right figure, we can see that we have, in the first case, this one, we have very high oscillation in the tank level measurement, and these are probably due to some valves that are regulating the oil flowing into cooler. While here on the right part, we have a very clean signal. So the analytics should be able to adapt itself automatically. Moreover, we have some huge peculiarities in our data, and these peculiarities, the most important ones are two. The first one is a discontinuity in the tank level measurement, and these are the refills. The refills are very important because we need to identify these refills and to reset the rate estimation in order to have a correct consumption rate calculation. So the analytics should be able to identify the refill. The refills are not always of the same size, of course. It depends on the customer, on the tank level geometry, and whatever. So the analytics should apply some statistical analysis on the data in order to identify correctly the refill. Another important aspect is a non-linearity in the data, that is the developing time. The consumption rate of an aeroderivative gas turbine should be quite stable during operation. But if there is some problem, these issues can go from an oil dripping, so just an abnormal consumption, till a broken tube. As I said before, the difference in the two signatures is very high. Here we can see that we have three different kind of problems, and they develop in a different way in terms of time. So the analytics should be able to react automatically to different kind of developing time. So the reactiveness should be automatically set by the analytic itself. Let's go on. Okay, how did we solve this problem? We tested many architectures, many analytics and techniques, but here, for the sake of brevity, I'm going to present you just the one that has been finally chosen. This one is the linear multivariate Kalman filter technology, and this technology is able to estimate the state of a system. The state of a system in this case is defined as the tank level and the consumption rate. And this system is able to estimate the state by combining the tank level measurement and a dynamic model of the system. So, and it does it in an optimal way. This is basically the mathematics behind the Kalman filter itself. So we have the measurement, that is the tank level here, with a refill actually. We combine this system with the dynamic model of our synthetic lube oil system, which is actually pretty easy, just a linear model with a constant rate. And of course, this is an assumption. And by combining the two, we are finally able to estimate the estimated tank level, which is highlighted in green. And as you can see, it acts exactly as a filter on the tank level measurement. And we are able to estimate also the consumption rate. Of course, this is about the dynamic model. This is an assumption that is not always true, especially when we have abnormal consumption rates and leakages. This is not true. So we actually added a feature to this system. It's not described in this presentation, but it is in the paper. We added a feature that is able to take into account for this kind of non-linearity by adding a correction part. It is basically a proportional regulator that is able to distinguish when the system, when the estimated tank level basically is deviating from the actual measurement. When this deviation is in place, the corrector start to work and to increase or decrease the consumption rate based on the, in order to correct this deviation. So we are now able to establish which is the estimated tank level and which is the consumption rate, actual consumption rate of the machine. Just one thing: the data is flowing continuously. So this system is analyzing the data and giving the outputs that we are seeing here continuously. So as soon as the data arrives, it processes and it does the estimation. So we applied finally 2 diagnostic rules to these outputs in order to detect 2 possible anomalies, 2 possible issues. The first one is the abnormal consumption rate. So the analytic continuously compare the actual calculated consumption rate versus a threshold. As you can see here, we have here the machine was operating, let's say, normally, so the consumption rate was kind of stable. Then after a stop of the machine, here some maintenance has been done. The tank level started decreasing in an abnormal way, and the consumption rate started to decrease, as you can see here. By applying a threshold, we were able to identify that here there was some abnormal consumption and to send an insight to our diagnostic engineer. Here, the very important thing is that this threshold here has been established by performing a fleet analysis. So we analyzed all the data coming from our gas turbines, and as I said, we have more than 300 under monitoring, and we were able to establish statistically which is the normal consumption rate. And we can exploit, let's say, this information to apply a threshold. And this is the first issue that we are able to detect. The second one are leakages. Leakages are pretty different from an abnormal consumption because they happen very fast in time. So as you can see here, the tank level started to decrease and it went down very rapidly. So here the analytics should be able to keep up with the actual leakage and to give an insight rapidly in order to let the customer take the necessary action to solve the issue, or at least to perform a normal shutdown instead of trip. And this can guarantee the correct lubrication and correct cooling of the components that we saw at the beginning of the presentation. So we can guarantee the lubrication and cooling on bearing, BSB system, and auxiliaries that are very important for the machine. We detected the leakage just by looking at the estimated tank level and the tank level measurement, and we can detect this high deviation here. When there is this high deviation, it means that there is a leakage in place. This deviation is performed statistically on the data, so the analytic is able to self-adapt and self-tune to the kind of noise in the data. This is a quite clean signal. And it is able to understand if this deviation is a normal deviation or not. So as you can see here, an analytic insight was sent to the diagnostic engineer, and they had the possibility to call the customer, call site operators, and let them fix the issues. So let's see the results of this system. But first of all, let's take a look at a normal M&D framework, let's say, a normal monitoring and diagnostic timeline. We have on the first subplot the tank level measurement in black, and in green we have the estimated tank level. On the second subplot, we have the estimated consumption rate by the Kalman filter, and on the last one, we have the turbine speed. Here, in this point, the machine starts, and we can see from the tank level, but also from the consumption rate, that we have a very low consumption rate, which is normal for this machine. This is a normal consumption rate, and the tank level is decreasing, let's say, normally. We expect a little bit of oil consumption. Then there is a refill here. As you can see, the system detects automatically the refill. It skips this point here, and it continues to estimate right after. Here, the machine is still working normally, let's say. In this point, there is a change in the tank level steepness, let's say, in the tank level measurement. The analytic was able to detect the deviation between the green line and the black line. It detected this deviation, that is a leakage actually. So the system sent to our diagnostic engineer an alert saying that there is a leakage in place. The diagnostic engineer called the customer, notified the issue, and let the customer take and suggested to the customer what action should be made. And actually, the customer had the time to perform a refill, organize the maintenance, stop the machine with a normal shutdown, not a trip, which is a very good thing to do for the customer. They inspected the system here during the shutdown. They inspected the system, they fixed the leak, and they start operating again. As you can see here, the Kalman filter, the consumption rate starts from here, which is the last point before the shutdown, and it aligns back to the original data. This is something that is very important because here the system does everything automatically. We don't need any reset here. So this is how we work, let's say, in our monitoring and diagnostic department. And here it is explained what is the actual use of this analytic. Let's now take a closer look to some real cases coming from our R&D department. Here we have a case of abnormal consumption rate. Also here we have, on the first part, this is the tank level measurement that we are seeing here, the black line. Here we have the normal consumption. As you can see, the tank level is quite stable. Then the machine was stopped. Right after the new startup, the analytic detected that the slope changed, that we have an abnormal consumption rate. And we send the insight to our customer here. The leakage was fixed, the tank was refilled, and the customer was able to continue without stopping the machine. In this case, the cause of the abnormal consumption was just a small leak on a drain point, so the customer just forgot to close a drain, so the drain was actually closed, and the customer could continue operate without any problem. If we compare the actual analytic insight versus the low tank level threshold that is used usually to monitor the oil in the tank, we can see that the analytic detected this problem around 60 hours before reaching the low tank level measurement. This 60 hours means 44.3 liters of oil that the customer saved, and this is a huge benefit in terms of operation, maintenance optimization, because we didn't have to stop the machine, and it has also some environmental impact because these liters of oil did not reach, let's say, the environment, but they stayed where they belong in the tank, basically. Let's now take a closer look to another case. This is a case of an actual leakage, and here we have the same information that we saw in the previous slide. So basically here the machine operated correctly without any problem. A refill was performed. Here, in this point, a leakage started. The analytic was able to identify the leak already here, so very close in time to this point. And our remote monitoring and diagnostic department was able to call the customer, tell them that something was wrong, so they planned a shutdown of the machine that happened here after some hours actually, and the customer who did, let's say, the maintenance identify a broken tubing here, and they started the machine again after fixing the tube. So the analytic detected that there was something wrong, there was a leakage in place, and there was, in this case, a broken tubing. If we do the same comparison with the low tank level approach, we can see that here we would have warned the customer around 1 day before the standard approach, and we saved 90 liters of oil with benefits on engine operation and the environment itself.
Okay.
Okay, so finally, yeah.
Almost on time, no? Okay.
Yeah. Just finishing very rapidly here. This system has been adopted 9 months from now on more than 300 engines by our R&D department. We sent 77 early warning to our customer, and actually the analytic did not require any fine-tuning. So the capability to self-adapt to the data worked as expected, and we received no request for update of this for tuning of this system. So thanks a lot, everyone, for your attention.
Thank you, Giuseppe. Thank you for your presentation. Very nice and clear. There are a couple of questions for you. The first one is, which is the frequency of data gathering necessary to effectively predict the anomalies? How is that frequency of data?
Yeah, actually, this can be, I mean, you can choose the frequency of the data, but in this case, we used 1 point per hour, making some aggregation in that hour, because the tank level can have some oscillation that we compress in 1 hour. So basically, the system is working with 1 point per hour.
Okay, and the second one, thank you very much. The second one is related to the instrument that measures the tank level. How do you deal with the miscalibration or the accuracy of that instrument? Is that so important to the model, the accuracy of the instrument itself?
Actually, the accuracy of the instrument is not important, and we can see that especially in this slide here. As you can see here, we have a lot of oscillations that I'm not sure if they are due because of the cooler system or because of miscalibration of the sensor itself. But the analytic adapts to these oscillations. So I mean, if we have a sensor that is giving that is oscillating a lot with a standard system, we would have a lot of false alerts by this analytic. While, but since we implemented this self-adapting capability, the system is able to recognize this oscillation, and it assumes that these oscillations are normal, and it goes on. Once the problem is fixed, if this is a problem, the analytic adapts again to the new data. So actually, we didn't have we didn't do any, let's say, research on the sensor types, but we focused more on trying to adapt to different kind of sensor, because these oscillations are not due only to sensors, but they can depend on operation and actually also on environment. So that is why we changed the approach here.
Okay, thank you, Giuseppe. And for the last one, we have a last question, that is, how did you calculate the abnormal consumption threshold of the system?
Actually, we performed a fleet analysis. We have more than 300 machines under monitoring, and we were able, let's say, to analyze the consumption rate from all the machines. We found actually that some machines, some type of machines, have a higher consumption rate with respect to other kind of machines. So we changed the threshold based on machine technology. For example, this is just an example, but let's say all the machines that are operating in a very cold environment have some consumption rate that can be considered normal, and we applied the threshold dedicated to this machine. So we were able to do some clustering on our data, and yeah, basically this is how it has been done.
Okay, Giuseppe, thank you very much, and thank you for